So today I'm going to discuss about the multi-component domino reactions which are triggered by novel condensation. So I'm going to give a brief introduction about the domino reactions, multi-component especially, and then I'm going to discuss about what we have been doing in our laboratory in this particular area. Before going directly to the domino reactions, I just would like to put a question. So, what is a synthesis? There are lots of definitions, but of course, you have reactants. You take some reactants and you add some catalyst or reagents, and you get the target. You get the product. So it's a specific sequence of chemical reactions. So it can be one step, two steps, or it can have several steps, which are called the synthetic steps. So this is like just like cooking in a laboratory. So in kitchen you cook to eat, but in the lab you cook to make new compounds. So why do you want to make a new compound? So why you bother synthesis? What's the need for synthesis? So it's $1 million question. Mainly because whatever the items that we use right from the morning until the night to go, to sleep, we are living with chemistry, especially organic chemistry. So consumer products, industrially important compounds, pharmaceuticals, you name it, you have all kinds of organic compounds in those products. So that is the main reason, one reason. The second one is that if you are a natural product chemist, then you identified that some extract of a compound, natural source, that is maybe it's a leaf or a flower or even animal extract or anything. So it has some activities against some disease. So in that situation, you can't again and again you can't go and depend on that natural source. So once you isolate that compound and you find that that one particular compound is responsible for the curing of a disease, then you need to make it in the lab. So in order to conserve the natural source, so you can't depend on the plant or the animal. So you identify the compound, you illustrate the structure, then you make it in the lab. So this is another important point to say why, to justify why you want to synthesize. And then there are several other points that if a compound is structurally, it attacks you, then you want to make it in the lab. So then you go for synthesis. And one more important point is that the structure-activity relationship. So if you discover a drug, if you discover a compound that and which has activity against any disease, then you can't stop in that one particular compound. So you need to make some changes around the system, around the rings, or maybe substitution. You make slight modifications, and you make several library of compounds, and then you check the activity and you come with the lead compound. So which is called the structure-activity relationship. So there, even in that area, this also justifies why you want to synthesize. And of course, if you are reporting a new mechanism, if you have done a new reaction, if you are doing, if you want to propose a mechanism as a proof, you need to isolate that intermediates, and you need to do the structural proof. So for that also, the synthesis is very important. So we have discussed why, what is synthesis and why we want to synthesis. Now there are good many people who have done a lot of work in this area, especially Woodward. So he was the first modern synthetic organic chemist, and probably is the greatest synthetic organic chemist until now. So he was awarded with the Nobel Prize for the synthesis of several natural products, like the reserpine, the cholesterol, etc. So you name it. It has come from the group of Woodward. And he joined hands with Hoffman in making the Woodward-Hoffman ring closure. So where the application of quantum mechanics to organic molecules came into picture. And in 1981, he was awarded a Nobel Prize along with Hoffman. So after that, the modern day Woodward is the K.C. Nicolov. So he is presently working in Rice University. So he is well known for the synthesis of taxols and toxins. So there are several compounds which are very complex in nature, and all these compounds are very much useful in treatment of some heart disease, the cancer. In this particular compound, this taxol, used to treat lung, ovarian, breast, head, and neck cancer. So this was isolated from a tree, and the structure was illustrated, and this compound, this taxol, was synthesized in the laboratory. So he is the modern day Woodward, I could say. And the routine drugs that we use, even starting from paracetamol to even the remdesivir, which is now given to the COVID-19 treatment, you have at least one heterocyclic system in that structure. So these are some few examples of the commercially available drugs which have been synthesized in the laboratory. So yes, you need to synthesize, but you also need to take care of the environment. So there should not be much thrown out in the environment as useless, which could again affect the soil and affect the environment. So you should be very careful. So here comes the concept of the green chemistry. So whatever the synthesis synthetic steps you do must follow at least a few principles of the green chemistry. So one such reaction or one such process is the domino reaction. So domino reaction means a reaction which involves at least two or more bond forming transformations, which takes place in the same condition, in the same pot, or you can say one pot, without adding the additional reagents or catalyst. So you add 2 or 3 reactants, and you just heat it or you leave it in the room temperature, you stir it, and after some time, if you get a new compound and you're not changing the condition or you're not adding any extra reagents, and those kinds of reactions are called as the domino reactions. So the domino reactions should start from at least one particular reaction, and the subsequent reaction takes place from the result of the functionality formed in the previous step. So there should be where you have the monocyclic triene, which affords the intermediate, and this intermediate has been converted to the progesterone. So here also it involves several cyclization reactions, and finally there is an elimination which affords and which has been converted to the progesterone. So then the two-component. So two-component reaction, you have 2 reactants which undergo several steps to give the desired product. Here, the best example is the Wheelan-Mischer ketone synthesis. So here, diketone and alpha-beta unsaturated ketone. In the presence of a base, you have a cyclic system, bicyclic system, so which undergoes through the mechanism as displayed here. Initially, there is a Michael addition taking place to give the Michael adduct, and then you have the cyclization, or you can say the annulation in the presence of the base, or the removal of water. So you take only 2 reactants. So you have 1, 2, 3, 4 steps to give the Wheelan-Mischer ketone, and this is well named as the Robinson annulation. So So here there is a domino michelation and followed by annulation and the dehydration steps altogether taking place in a single pot. So this reaction was used for the synthesis of cyclohexanones. So there are several reports. I have taken one report from the Angu Chem. So here again there is by the annulation and then the elimination here does not occur. So there is just two steps, or we can say when you heat it, it may undergo the dehydration, but it has been done in ambient temperature, and you get the alcohol, not the dehydrated ketone, alpha beta unsaturated product here. So here it involves a domino michelation followed by annulation, which again is called the Robin reaction. Reactions. So one component, two component, yes. Now if you have more than three, or you can say more than two, those reactions come under the category of multi-component domino reactions. So domino reaction involving at least three substrates. So here the multi-bond transformation formation in a single vessel occurs, and the product will have the components of all the reactants. So if the product is devoid of any one of the component, you can't say it is a multi-component. So the product should have at least a small part of each component that has been used as the reactant. Now the starting material for these chemicals, it should be rich in functional group so that the subsequent reaction takes place very easily. And it leads to complex products from simple starting materials. And of course, this multi-component domino reactions should be initiated by any one reaction. So the common reactions are michelation, heteromichel, aldol, novenagel. So these are a few of the examples of the multi-component domino reactions which are initiated by a specific reaction. Now, here are the few examples of classical multi-component reactions. So we have read, we have studied for many times these reactions, and which we forget to classify them as multi-component domino reactions. So the first and the basic reaction is the Hans pyridine synthesis or dihydropyridine synthesis. So here it involves a four-component, kind of pseudo four-component reaction. So beta keto ester. So 2 moles of beta keto ester, an aldehyde, and then amine, in this case ammonia, you get dihydropyridine. So you can see you have 4 components, and the product has the the parts of all the 4 reactants. So such reactions can be categorized as a multi-component. Here in this case, it's a 4-component domino reaction. This presumably it is the first multi-component domino reactions that have been reported in the literature. Now here the mechanism involves the formation of the novenagel adduct initially, and then you have the nucleophilic addition of the ketone and the ammonia to form the enamine, and then followed by the michelation between these 2 intermediates, and cyclization takes place, and an elimination takes place at the last step. So totally there are 5 important key steps occurring in this Hans dihydropyridine synthesis. So this is a classical example of multi-component domino reaction. And then the bigenol. This is also a very common reaction, which where we are well aware that it leads to the formation of the pyridones, which are biologically very important. And here again, there is a keto ester, an aldehyde, and urea, or you can use thiourea also. And there are 6 steps involved in this reaction. Initially, the nucleophilic addition between the aldehyde and the urea, the diamine, and followed by the dehydration, removal of water. And then in the acidic condition, the ketoenol tautomerism takes place. It's also included as a step. And then the addition of the enol to the carbon of the imine leads to the intermediate, the amine here, amide in this case, and followed by the cyclization and the subsequent removal of water. So there are 6 steps involved in bigenol. So it's a 3-component reaction which occurs through a 6-step transformation in a single step in a 1-pot process. Of course, there are several modifications of these classical reactions now, which are categorized as domino reactions. And then you have the common, the very famous Manich reaction, which leads to the Manich base. So here also it's a three-component reaction between an aldehyde or a ketone and a secondary amine, which leads to the Manich base. So this is a four-step reaction. Again, there is a nucleophilic addition occurring and the dehydration, and then the enolization in the presence of the acidic conditions, and then finally the addition to imine carbon leads to the desired Manich base. So this is again an example of the classical example for domino reaction. And this Manich reaction was very helpful in the synthesis of tropinone, so which was a very important drug in the World War I. So initially, this tropinone was synthesized. The tropinone, it was actually the intermediate for atropine. So this tropinone was initially synthesized by Richard Willstater in 1903, but it required 15 steps. But later on, Robinson just imagined that this tropinone can be broken into three parts: a dialdehyde, an amine, and a ketone. And this compound can be synthesized in one step. So just by there involves a double Manich reaction, which leads to the tropinone in one step. So just imagine where is 15 steps and one step. So this domino reactions are very much helpful in synthesizing compounds, which is another example of the domino reactions. So these are few examples of classical examples of domino reactions, which we have already learned, but not in the category of the multi-component domino reactions, but it is. Now we are going to focus on the multi-component domino reactions, which are triggered by the Knoevenagel condensation. Yes, Knoevenagel reaction is a well-known reaction. So it leads to an important intermediate, which is very reactive intermediate. And this alpha-beta unsaturated system can be used as a reactant, or it can in situ. If it is generated, it can be used for several other reactions, starting from the Ene reaction, or the Michael addition, or the hetero-Diels-Alder, or the Diels-Alder for that matter. It can involve 1,4 addition because it's an alpha-beta unsaturated system. So you can explore the 1,4 addition also. And addition elimination, dipolar cycloadditions is also very much explored. Even we have been doing several azomethyl halide cycloadditions using this Knoevenagel adduct. And there are several examples of the utility of this Knoevenagel adduct for synthesis of several complex compounds. And here are the few examples of the Knoevenagel adduct which have been reported in the literature, and of course we also use a few of these. And here is one example which involves the initial Knoevenagel and followed by Michael addition. So this was reported in JOC in 2000. Organic Letters in 2010, and it's a three-component system reaction which affords the spiropyran derivatives. Now, how it takes place? So you can see that you have the components, all the three components here, the parts of all the three components, and that's a mechanism suggested, and it undergoes an initial Knoevenagel condensation between the diketone and the malonitrile in the presence of the base, and then this Knoevenagel adduct, it undergoes a Michael addition involving the diketone and the Knoevenagel adduct, and which is followed by the cyclization, which involves the oxygen and the amine carbon to form the product. So it involves a Knoevenagel, Michael, and cyclization in a single step. Now we'll discuss about what we have contributed in this area, in this type of research. Now we chose to synthesize pyridine derivatives by modifying the Hans dihydropyridine synthesis. So we know that the Hans dihydropyridine synthesis involves four components: diketone, 2 moles of diketone, an aldehyde, and an amine. So there is an initial novel condensation, and you have the nucleophilic addition, and finally there is a michelation between these two to form the pyridine. Now we have just used different kinds of reactants to explore the synthesis of pyridine systems, the fused pyridine systems, the usage of hetero ketones, cyclic ketones, and malonitrile, aldehydes, and ammonium acetate or the amines. First, we saw in the literature that a fused cyclooctane pyridine system is used as a drug, so which is gonanserin, so which is commercialized by schizophrenia. So it's a brain-related disease. So we wanted to make analogous of this compound, and we took the cyclooctanone, aldehyde, and malonitrile, and we thought, using ammonium acetate as nitrogen source, we could synthesize this analogous of the gonanserin system, the fused cyclooctane pyridine system. But in this case, we were not successful, but we got another compound, which here the nitrogen is not involved in this reaction. We got the benzene fused cyclooctane systems. So again, through the literature, we saw that the only natural product which had the core of the cyclooctane fused benzene systems are the parvifolene and the isoparvifolene. So we explored to synthesize several compounds of this, and we optimized the reaction condition, and it involved 2 moles of the malonitrile. So it's a kind of pseudo 4-component domino process, and this reaction was done on water reaction, and we got very good yields of the product, the analogous of the natural parvifolene and isoparvifolene. So we were able to do 20 examples of this compound, and fortunately the student was working hard to get several crystals of this compound, and so she succeeded. This was helpful in elucidating the structure of the compound. And we need to propose a mechanism, and we thought that initially the presence of the base, there's an novel condensation involving the aldehyde and malonitrile, and simultaneously the ketone and the second mole of malonitrile, giving the 2 novel adducts 5 and 6, and then subsequent the michelation between these 2 intermediates, and kind of Thorpe-Ziegler cyclization followed by the elimination, we get the product. So this was the first reaction that we explored in this context, and then we wanted to make that compound, so the gonanserin analogous compound. So just we made a slight modification by using by changing the solvent and reducing the the quantity of malonitrile. So the same reaction we performed, and we thought we could get the targeted pyridine fused cyclooctane. But even here we got a kind of different compound, and it's a slight modified compound that we expected. So the alcohol or the solvent that we used, it was the 4th component involved in the reaction. So whatever the alcohol we use, so that is being substituted alpha to the nitrogen. So again, in this case, the student was successful in making several crystals, single crystal studies. So we illustrated the structure, and then we had to propose the mechanism. And as usual, there's an initial novel condensation, and followed by, in this case, the second novel is not taking place. The michelation occurs, and in between here, there is the nucleophilic addition between the alcohol and the imine carbon, which leads to this intermediate 10, and followed by the cyclization, and the dihydropyridine, the presence of air, it leads to the more stable aromatic system. So the compound was isolated. And again, we made a slight modification to make the nitrogen substituted side chain as present in the guanine. So we used in this case, of course, the solvent the same was ethanol. So we thought that this nitrogen could can overcome the substitution that was occurred by the solvent. So we thought that this would come first, and so we took this benzylamine, and we expected. We expected the nitrogen side chain as shown here. So the benzylamine would make a nucleophilic addition over the imine carbon, as we discussed in the previous case. But again, we did not get this the expected product, but we got an interestingly different compound, and an amine. We got an amine as the product, and the structure again it was confirmed from the single crystal X-ray, and it was confirmed that the presence of amine is here. And the NMR studies of this compound led to an interesting point here, interesting observation. So here at room temperature, the CH2, the benzyl CH2, it gave a broad singlet here. So 298 Kelvin, you can see that here it was a broad singlet. So initially we thought that yes, this compound was formed and this NH was broad, but the absence of this CH2, it was confusing us. And later on we found that there is the N14 quadrupole relaxation taking place. So this N14, it's a quadrupole nucleus, and it it relaxes these CH2 protons very fastly, and this CH2 protons, it appeared as a broad singlet here. So we in literature we studied that we learned that when you increase the temperature, the quadrupole relaxation is nullified, and you can get sharp singlet or the sharp signals for the affected proton. So as studied, we did the variable temperature NMR, and you can see that gradually when we increase the temperature, the CH2 singlet appears as a sharp signal here at 333 Kelvin. And we wanted to do the low temperature NMR, so for some reasons which I will discuss later. And as we reduce the temperature and when we come to 233 Kelvin, you can see there is two doublets formed, because the NCN bond rotation, it is arrested, so that these two CH2 it becomes diastereotopic, and you get two doublets for these two CH2s. So by that we confirm that the presence of N14 quadrupole relaxation is there in this compound, and this was an interesting observation while we did this reaction. So we had to propose a mechanism, and the key intermediate here is the intermediate 9 shown here. So the initial steps are the Novenagel and followed by the Michael to give the Michael adduct, and also the expected nucleophilic addition takes place between the amine and the imine carbon, and this is the crucial intermediate. So here there's a choice between the cyclization between either the primary or the secondary NH. So if it goes through path A, so between the the cyclization occurs between the secondary NH and the oxygen, so that will lead to the product which we expected. But the reaction did not go in that way. But the cyclization, it took place between the primary amine and the OH, the ketone, to form this intermediate 10, and it follows by the dehydration, and finally we have the air oxidation to form the the compound which was unexpected, the imine. So we explored this reaction, and we made 17 examples of these compound, and of course again we illustrated the structure by single crystal X-ray. We wanted to further explore this reaction in the lower ring size ketones like cyclopentanone, hexanone, and heptanone. And we expected the product which was formed in the case of cyclooctanone, but here unexpectedly we got the product which was expected in the previous case. So that is the cyclization takes place between the secondary amine. So we got the other way around. So again, in this case, we illustrated the structure and we had to propose the mechanism. And here you can see between the primary amine and the ketone, which led to the formation of the unexpected in this case. So we were successful in making compounds which were analogous to the drug, the glumancerin. And as I discussed later, so we did the low temperature NMR to explore a kind of observation. Another observation in this case, here we can see that the cases of the phenyl ring here, which had substitution in the 4 position or without any substitution, there was only one broad singlet because of that CH2, the benzyl CH2. But once if the phenyl carried an ortho substitution or the ortho para disubstitution, there were two broad singlets in this case. So which was in the cyclooctanone case, there was the influence of N14 quadruple movement, so that the benzyl CH2 was the CH2 appeared as broad singlet, and here we got 2 singlets, broad singlets, but we expected that it was due to the diastereotypic nature, because there is a restricted rotation of the CC bond in the case of ortho substitution. So there is a steric hindrance between the cyno and this ortho substitution, which restricts this rotation. So there's a chiral axis involved here. So it leads to the attrop isomerism, and the compound is chiral because of so the isolation progress now. So we have collaboration with a group in Italy, which is presently doing, because of this COVID situation, it has been temporarily stopped. So we are trying to isolate these 2 isomers and to study the structural features separately. So I can't discuss it now. So once we get the results, I will be happy to share with you again. And in the case of lower ring systems, I can see that we observed that there was no N14 quadrupole relaxation. And you can see that in the case of the ortho substituted rings here, this CH2 becomes diastereotopic, and it has a geminal coupling, giving a doublet, and there is a coupling involved with vicinal coupling involved with this NH also. So which leads to 2 doublets of doublets for the CH2, and this NH is split into a triplet. So these observations were very interesting when we did this reactions. In all the cases, you can see that ortho substitution, because of this restricted rotation, the compound is becoming chiral. And then we wanted to further extend the same reaction with higher ring systems. So in literature, we saw that the pyridine-fused cyclododecanes are used in perfume industries and also as some drugs. So we wanted to make such systems through our multi-component domino reaction. So we took the cyclododecanone, aromatic aldehyde, and malonitrile, of course, and ammonium acetate as the nitrogen source. So when we did this reaction, we observed 2 different products. So one is the pyridine, and the other one is the unaromatized tricyano systems, the fused cyclododecane and the kind of benzene system. And of course, we got the reaction between aldehyde and malonitrile is an intermediate form in this reaction. So we wanted to tune the reaction in such a way to isolate these 2 compounds differently, as you know, as exclusive product. So what we did is we explored the usual reaction, the cyclododecane, tecanone, aromatic aldehyde, and the malonitrile. In toluene, in the presence of ammonium acetate, we were successful in making the targeted compound exclusively, the cyclododecane fused pyridine systems, and the structure was illustrated by Cindy Pistol. And then by tuning the base, by changing the base from ammonium acetate to piperidine, we were able to get the tricyano system, the unaromatized tricyano systems exclusively. And this was done under room temperature. The same reaction when we carried out in, yes, of course, the reaction, I mean, the product was confirmed from single crystal. And the same reaction when we did this reaction under reference conditions, the elimination takes place and we get the fully aromatized benzene fused cyclododecane compounds. So this was very interesting. Even in these cases, wherever you have this aromatic ring, I mean, two substitution in the aromatic ring system, there is the axial chirality involved in such cases. Now, the next, we wanted to introduce an indole system in the fused pyridine fused cycloalkane rings. So, as one of the reactants, we took the indole acetonitrile as the source and aromatic aldehyde, and you have the cyclododecane and ammonium acetate as the nitrogen source. So we were successful in synthesizing 23 different compounds of the indole tethered pyridine fused cyclododecane rings. And again, it was the structure was confirmed from single. And when we explored in different ketones, cyclohexanone, heptanone, and octanone, we got the desired compounds in good yields. So here again we illustrated the structure from NMR and ultimately from the single crystal X-ray. By the meantime, when we explored the synthesis of cyclohexane fused pyridines or benzene system, we wanted to make the hetero systems, like the fused system, the fused ring contained heteroatom. So by that way, we first explored this diffused thiophenone, the thiophenone, malonitrile, and the aromatic aldehyde as we discussed in the first example. So we got the benzene fused thiophenone ring system, and this compound, one of this compound, we found that it inhibits the ACHE. So this cholinesterase is, it's an enzyme which is helpful in reducing the Alzheimer's disease. So of course, this compound was less effective than the commercial donepezil, but we were, able to find out the lead compound in this case. So further studies are going on, presently to identify more potent compound of this kind by changing the substitutions and the by introducing the pyridine system. We are presently doing the research under the collaboration with the University of Malaysia. In the next work, we tried to introduce, another ring in between the two, the pyridine system and the heterocyclic system. So we synthesized this fused pyrazole fused ketone, and then as usual we did the same reaction. So in this case, under microwave conditions, we were able to synthesize 11 examples of the pyrazole quinoline carbonitriles. So in these cases, again we observed the same axial chirality in ortho-substituted ring systems. So initially in the para substituted aromatic aryl rings, we got two triplets for the two CH2s, this 5 and 6 CH2s. It was clearly giving us two triplets. But once meta substitution or naphthyl or orthochloro substitution, the splitting pattern changes. So these two CH2s becomes diastereotopic because of the axial chirality, and then it is split into multiple signals. And here we observed these compounds exhibited fluorescence under UV. And here you can see that this compound, this particular compound, in this case, the methoxy substituted aryl, here in this particular example, if there is a methoxy substitution, the 4-methoxy substitution exhibited fluorescence, and it detects iron 3 plus in the presence of different metals. And excuse me, in the presence of other metals, we found that this compound was selective to detect the Fe3 plus alone. And we proposed the mechanism, the quenching mechanism. Initially, the fluorescence was turned on because of the ICT involved between the. I should show the structure. So, because of the, so this is a donor system and you have the acceptor system. So there is an ICT involved in these two, which was found through the DFT studies. So you can see the HOMO-LUMO difference here. It was around 4.03 electron volt. You can see the distribution of the HOMO and LUMO. So there is a slight ICT involved here. Distribution of the HOMO and LUMO. So there is a slight ICT involved here. So that results in the formation of, in the fluorescence, and which was quenched because of the interaction between the amine group and the ion here. So which inhibited this ICT, and totally the fluorescence was quenched in the case of Fe3 plus alone. And the other metals were not, the fluorescence was not quenched. And so in the daylight, it was colorless, and under UV it was somewhat blue, and then finally the fluorescence got quenched because of the amine with the Fe3 plus. So this was another observation that we explored while doing our multi-component amino reaction. And then the next reaction that we explored was the Pirido. So in the previous case, it was a 5-membered fused cyclohexanone system, and in this case, it's a 6-membered Pirido fused cyclohexanone system. So initially we synthesized this intermediate, and then in this case, it was not. We were not successful in making the domino reaction because of several reasons. So we made the intermediate separately, and then the reaction of this 3 and 6 in the presence of ammonium acetate. So it's a 3-component system in this case, and we were able to make 3 different compounds, and all the 3 compounds exhibited very good fluorescence. And so we were, we found that this sensing any metals. So for that matter, even Fe3 plus, it did not detected by, or the fluorescence was not quenched with the presence of any metals. But we found that this compound sensed picric acid. So you can see that the fluorescence was quenched in all the 3 by all the 3 compounds. So we introduced different kinds of nitro compounds, and we found that this compound selectively sensed the picric acid. So the graph shows the selectiveness of this compound in sensing picric acid. And we proposed the mechanism, which I will discuss in the later example. And we thought, that the presence of this aminopyridine itself will exhibit fluorescence, and we wanted to make the free pyridine ring system. And in this case, we used the furan acetone, acetylfuranone as one of the reactant, and then we did the same reaction, and we made 4 different compounds. And of course, the structure was illustrated by single crystal X-ray. And here we found that out of these 4 compounds, 2 compounds were fluorescent under UV lamp, and the other 2 were not. So maybe the presence of the electron withdrawing group, the nitro group, the compounds did not exhibit fluorescence. So we explored the sensing ability, and we found that this compounds, the fluorescence quenched in the case of Fe3 plus, as we discussed previously. and the selectivity was also studied. And a similar DFT studies it proved that there is an ICT involved. The homolomo pictures here, you can see there's an picric acid. And while proposing the mechanism of quenching, we thought that there can be hydrogen bonding involved between this nitrogen protons, hydrogens, and the oxygen of the picric acid. So because of that, the ICT is being quenched, and the fluorescence is again quenched. So we did the NMR titration experiments, and we found that that was the exact reason, because you can see the amine peak of the free probe. It appears at 5.33 ppm, and when gradually we added the picric acid in different mole ratios, in the 1:1 mole ratio, so it is deshielded and it appeared at around 6.48 ppm. So we confirmed that this hydrogen bonding is involved, and a kind of picrate is formed, so which inhibits the ICT, and the fluorescence is quenched. And you can see in this case it is around more than 1 ppm shift in the of the signal, of the amine signal. So similarly, we proposed the mechanism for the previous examples, which the compounds which detected the picric acid. And then by exploring substitution, so in the previous case we had the furan as substituent, and here we changed it to phenothiazine. So phenothiazines are well known as they are used as OLEDs in making OLEDs, and their photophysical properties have been studied very well. So we wanted to introduce the phenothiazine moiety into this built-in system, and we thought we could get good fluorescence in this case. So the acetophenone of the phenothiazine was used as the reactant, and we were able to make this compound under the microwave conditions. So again, it's a 4-component downward reaction, and we got this compound in a good yield. That this compound was fluorescent in solid state. So this solid state fluorescence studies is again we are doing it in collaboration with Dr. Jayantinath from Material Science. So he's he's in Oslo. So we are doing the solid state fluorescence studies under the collaboration with the University of Oslo. So that results again we are expecting very soon. But I will just give a slight what we have done here. Now this compound in various solvent, you can see from the benzene to DMSO. So it depended on the polarity of the solvent. So the color changed depending on the polarity. But finally we chose DMSO because there was it was very fluorescent, and we had we thought that it will be helpful to study the metal interaction and also the picric acid studies. So now here we took this compound and we studied, and you can see that in the process of various metal, only Fe3 plus was it was successful in binding with the probe, and the selectivity was again studied, and we discussed the mechanism, the quenching mechanism, which again it involved the inhibition of the ICT, which was there in the probe, and the binding of the metal, it inhibited the ICT, and thereby it quenched the fluorescence of the probe. Again, it was a dual detector, and we found it is able to detect picric acid. So the presence of different nitro compounds, we saw that we observed that this compound selectively detected the picric acid. And again, in this case, we did the NMR titration, but we clearly saw that the formation of the picrate So because the amine peak, which appeared at 5.92 ppm, by gradual addition, you can see that the amine peak is completely vanished, and that's a picrate salt which was formed, and we confirmed it. It was the picrate salt which was formed, and the interaction of the amine with the oxygen of the picric acid, the hydrogen bonding involves, and the fluorescence quenching was took place because of that hydrogen bonding. So I think I should finish now, and I should acknowledge several people. And first and foremost, I would like to thank Professor P.S. Mohan, the former professor and head department of Chemistry-Bharathiar University, and the present SDF member. So again, I would like to tell that he's an inspiration to me, and I would like to thank Dr. T. Suresh and Dr. A. Kannan, the organizing secretaries of the RTC 2021, and Dr. Prabhakaran, Dr. M. Kaveri, Dr. Selvaraju, and Dr. Ilanjalian, the convener and the HOD of Department of Chemistry, Bharathiar University. And of course, the MKU for giving me this opportunity to discuss with you, and UGC and DST for giving funds for the work, and again the DST for the 300 megahertz instrument NMR spectroscopy here, and of course the INSPIRE program, and of course there were several people involved in this work. I would like to thank all the people. So, and again, I thank all the participants here who are, humble and listening to me in this final day of this RTC. So, thank you one and all. And maybe I would like to, I'll be happy in answering a few questions. Thank you.
Dear participants, if any of you have questions, then you can ask the resource person. Thank you.
Sir, this is Murugesh Pandey, sir.
Yes, sir.
Thank you, sir, for nice presentation. Sir, the carbosol, no, phenothiazine derivative, no?
Yes.
That is act as a iron turn-off sensor.
This one, yes. Yeah. Yes, exactly.
Okay, sir, okay. It's the coordination site is the pyridine, hydrogen, and amino.
Yeah, the amino and the pyridine. We did the DFT by involving these two, and of course that is one of the proposals. So it can also involve the interaction with this NH, but we propose that this amine and this NH2 involved in the coordination between the metal.
There is a possibility and NH2 may it's like a chelation
can happen, yes. But we should not do
carbon free rotation.
Yes, exactly. This you mean this carbon. Yeah.
So all the things are turn-off sensor.
Yes.
Iron.
All the this pyridine, the 2 amino 3 cyano-pyridine systems, whatever we synthesized, all these compounds we found that it is a turn-off probe.
Okay, sir. So any other question? Any clarifications? If there is no question, I would like to thank Professor Ranjit Kumar for a very nice presentation, and it's excellent explanation and about the mechanism and how the domino reactions can be used for the various molecules with the different properties like acetyl coenzyme inhibition and chemosensor and blue emitting materials kind of. Thank you, sir. Thank you for a very nice presentation and clear explanation. Thank you, sir.
Thank you very much, and I should thank all the participants for listening throughout this time, and I hope you had a nice session, and maybe if you want to clarify anything, you can also mail me. Thank you.
Sure, sir. Sure, sir. Thank you, sir. Thank you, sir. Thank you very much.
Thank you very much.
Thank you, sir, for the nice presentation. Dear participants, please note, kindly fill in the feedback form and submit before 2 p.m. The afternoon session is at 2 p.m. Kindly join by 1:45. Speaker is Dr. Ganesh Chandra Nandi. After the session, there will be valedictory session. Please use Google Meet link to join. If unable to join, please use YouTube link also. Thank you.